Let's dive into regularization techniques in the world of neural networks. What is regularization anyway? Well, basically, regularization is any technique that is intended to prevent overfitting. What is overfitting? Well, if you have a model that's good at making predictions on the data it was trained on, but it doesn't do so well on new data that it hasn't seen before, then we say that that model is overfitted. That means that it's learned patterns in your training data that don't really exist in the general sense in the real world. So if you see a high accuracy on your training data set, but a lower accuracy on your test set or your evaluation data set, that's nature's way of telling you that you might be overfitting. Let's take a step back here. This is probably the first time I've used the word evaluation data set. Again, if you're new to this world, in the world of deep learning, typically we talk about three different data sets. So we have the training data set. This is the actual training data fed into your neural network from the bottom up, and that's what we actually train the network on, right? And then as we're training each epoch, we can evaluate the results of that network against an evaluation data set. So basically, that's a set of the training set that's set aside to evaluate the results and the accuracy of your model as it's being trained. And then we can also have a testing data set that lives outside of all of that. So once we have a fully trained model, we can then use our testing data set to evaluate the complete finished model, if you will. So again, if you're seeing your training accuracy being a lot more than the accuracy measured against your evaluation data or your testing data at the end, that probably means you're overfitting to the training data. This graph on the right here makes it a little bit more easy to understand. So imagine I'm trying to build a model that just separates out things that are blue from things that are red here. So if you eyeball this data, your brain can pretty much figure out that there's probably this curve that kind of separates where the bluish stuff is and where the reddish stuff is, right? But in the real world, data is messy. There's a little bit of noise there too. So if a model were overfitting, it might actually learn that green curve there that's actually snaking in and out of all the data to try to like fit that training data exactly. But you know that's just noise, right? I mean, just looking at it, your brain knows that that's not correct. But your neural network doesn't really have that intuition built into it. So we need regularization techniques to sort of prevent that from happening, to prevent a neural network or any machine learning model from curving and undulating and sort of making these higher frequency pass out of the way to overfit its data to its model. All right, that's what overfitting is. It's a good way to generalize it. The so-called correct answer, the correct model, would be that black line, but an overfitted model would be more like the green line. And this is actually something that really happens in neural networks. If you have a really deep neural network with lots of weights and connections and neurons that are built into it, it can totally pick up on complex patterns like that. So you do have to be careful with it. So that's where the world of regularization techniques come in. Let's go into some. So a very simple thing might be you might just have too complex of a model. Maybe you have too many layers or too many neurons. So you could have a deep neural network that's too deep or maybe too wide or maybe both, right? So by actually simplifying your model down, that restricts its ability to learn those more complicated patterns that might be overfitting. So a very simple model that's just a simple curve like that could probably be, achieved through a regression. Maybe you're better off with a simpler model. And the simplest regularization technique is simply to use fewer neurons or use fewer layers. That is a totally valid thing to do. Sometimes you need to experiment with that. So if you find that your model is overfitting, probably the simplest thing is just to use a simpler model. Try fewer layers, try fewer neurons in each layer, and see what kind of effect that has. If you can still have the same accuracy in your test data set, but not overfit to your training data set, then why use more neurons than you need? Another technique is called dropout. And this is kind of an interesting one. So the idea with a dropout layer is that it actually removes some of the neurons in your network at each epoch as it's training. And this has the effect of basically forcing your model to learn and spread out its learning amongst the different neurons and layers within your network. So by dropping out specific neurons that are chosen at random at each training step, we're basically forcing the learning to spread itself out more. And this has the effect of preventing any individual neuron from overfitting to a specific data point, right? So it's a little bit counterintuitive that actually removing neurons from your neural network can make it actually train better, but that's what happens. That prevents overfitting. So that's what dropout is all about. Again, a very effective regularization technique. We see this a lot in, say, CNNs, for example. It's pretty standard to have a pretty aggressive dropout layer, like maybe even 50% being held out for each training pass. So that's all dropout is. It's just removing some neurons at random at each training step to force your model to spread its learning out a little bit better. And that has a regularization effect that prevents overfitting. Another very simple solution is called early stopping. So let's take a look at this printout as we're actually training a real neural network. So you can see that if you look at the accuracy on the validation set, that's the right-hand column there, we're going from 95% to 97%, and things are getting better. And then all of a sudden we get up to like around 98% and things start to get weird. It starts to oscillate, right? So we can say just by looking at this that after around epoch 5, we're not doing any more benefit by training further. In fact, we might be doing more harm than good because at this point we're probably starting to overfit. And indeed, if you look at the training set accuracy, that's that first column of accuracy, the second column of numbers that you see in this display, the accuracy in the training set continues to increase as we train more and more epochs. But the accuracy on the validation set pretty much stopped getting better at around epoch 5. So this is pretty clearly starting to overfit beyond the fifth epoch, all right? All early stopping is a way of automatically detecting that. And it's an algorithm that will just say, okay, the validation accuracy has leveled out. My training accuracy is still increasing. We should probably just stop now. So early stopping just means, okay, I know you wanted 10 epochs, but I can see here that after 5, things are just getting worse as far as overfitting goes. So we're going to stop at 5, guys. We're done here. That's it. That's all early stopping is about. It's just making sure that you're not training your neural network further than you should. And that prevents overfitting. Very simple solution there.